What about noise? What about complaints of noise, cabin whine, whistle? These are all higher frequencies. We've got a case study here that we can replicate. That is what turned out to be a cooling fan issue. But the story goes that minor accident damage, front end of a vehicle. Body repair is perfectly fine, but at certain moments there is quite an intense vibration passing through into the cabin. So this is where, if it's a complaint of noise, then we should include the microphone. We can still use the accelerometer, but let's add the microphone and place that in the cabin, ideally next to the driver's ear, if it is them who is complaining of the noise, or maybe rear view mirror, because that will give us an overview of all the noises present in the cabin during the road test. So let's have a look at this animation. So here then we're adding the microphone to channel D. There we have the issue. This was damaged cooling fan, and here we're displaying the noise in bar graph view. So you can see there we've got the vibration, the intense vibration that comes on when the cooling fan comes on at top speed, and we're displaying there the bar graph view. On the right hand side you'll see the top 5 unknown vibrations, and that's unknown because it's not linked to engine or road speed. It's an electric cooling fan.
So what I've picked up there from the bar graph, Steve, is that it is an unknown frequency. It's not related to anything that we're able to synchronise from known data from the vehicle setup.
Yeah, that's exactly right, Frank. And the view we've chose there, on the right-hand side, the bar graph view is showing the top 5 unknown vibrations. We've highlighted vibration 1, 39 hertz it is, peak vibration detected by the accelerometer in the vertical axis, but also detected by the microphone inside the cabin. So I think we're certainly tuned into the customer's complaint. Let's go and replicate this on our van. So what we've done here with the van is simulated exactly what you saw in the animation. We've introduced a deliberate imbalance to the cooling fan. We've also then introduced the microphone into the cabin. So not only will we measure the vibration, but we'll measure the sound, which, remember, is one in the same thing. The microphone and the accelerometer both detect the vibration, the sound generated, and display them differently, but at the same frequency. So we can use either or in this scenario. Certainly this would be your choice of measurement for chasing a transmission whine, for example, or brake squeal, anything sort of above 200 hertz.
So really this technique is for indiscrete noises which really can't be easily identified to a particular component.
Yep. Okay. So connection-wise, we've gone for 3-axis plus single channel. So still use one accelerometer measuring all 3 axes. But the additional channel now, channel D, is the microphone connected to the rear view mirror. So in a road test example, the microphone will detect all noises, but there's a specific noise we're chasing here, which is the noise generated from the imbalance in the cooling fan.
And I guess from this setup, would you also recommend moving the position of the microphone once you're honing in on the noise to perhaps increase the amplitude of the results?
Yeah, the opportunities are endless really, because certainly always keep a microphone in the cabin as a reference, because that's what the customer can hear. Perhaps keep one in the cabin, one in the engine bay, and also keep the accelerometer as well, so you've got 3 points of reference really. Think of bearing noise if you've got the luxury of 4 microphones, 4 accelerometers, 1 road test, 1 measurement with a reference inside the cabin.
Would you also recommend multiple microphones in the same way you would accelerometers?
I would, most certainly, yeah. The advantage really of the accelerometers is we lose a lot of the ambient noise. However, the microphone gives a real, true representation of what the customer can hear. Mm-hmm. So always include a microphone in these kind of measurements as your customer reference, as a kind of an indication, a representation of what the customer can hear. So the setup here for the cooling fan noise vibration, we've gone for a static RPM. Remember, we're not road testing, we're not looking for a vibration relative to engine or road speed. We've gone for a 3-axis plus single channel measurement. 3-axis is our accelerometer mounted to the driver's seat, and the microphone is up at the rear view mirror. That's giving us the customer's audio reference, if you like, what the customer can hear. So if we go to record and analyse, we'll restart the recording because we've got previous data here. There's a warning there to let you know that if you do restart the recording, anything you have here is now lost. We'll start the recording here. We'll use the auto scale feature, and we'll let the software, the scan tool software, run the cooling fan. Okay, if we can stop the cooling fan there, we'll pause the software, and we can then drag our highlighter here, pull that onto the offending area, which is this area here. Use the right-click auto-scale feature, and we can see that both the accelerometer and the microphone have picked up the frequency, the offending vibration noise that the customer can hear. We can just use the channel in view and concentrate on the audio. So channel in view enables us to take away channels A, B and C, which is our accelerometer. And we're left then with this offending frequency, the highest peak in the spectrum. This is approximately 38 hertz, 36 hertz. This is our offending frequency. So
now how can we, Steve, we've got this 38 hertz,
yeah.
How can we then relate that to a specific component?
Right, it's a great question. I mean, we know that that is the peak that we've captured during the vibration, during the noise. We know that frequency and speed are directly related. Hertz times 60 is RPM. Well, we could actually use the speed of the cooling fan, because if we've got one disturbance from this cooling fan, remember in the animation there's a blade missing. On this cooling fan we've added weight. One disturbance per revolution. Let's use an optical pickup on the fan, which theoretically should give us a frequency of about 36, 38 hertz.
So just using an independent, handheld, optical
pickup.
RPM interface?
Yeah, using PicoScope.
Right.
So how have we created the imbalance in the cooling fan here? Well, simulating what you saw in the animation, a missing blade, we've placed a bolt through this blade here. So for one revolution of the fan, that will create one disturbance. How can we determine the speed, frequency of this fan? Remember, speed and frequency, one in the same. We attach some silver tape here and point the optical pickup at the cooling fan. So every time the optical tape passes the optical pickup, it generates one pulse per revolution. That will give us the frequency of the fan. We can then use PicoScope to not only count those pulses but display the frequency of those pulses, which should come out around about 36 hertz, because that's what we captured our vibration, our peak amplitude vibration at 36 hertz in NVH. So using the optical pickup to determine the frequency of the cooling fan, we'll connect that into channel A of PicoScope, run the cooling fan at the top speed, there is only one speed setting for this one, and see what PicoScope displays in terms of frequency. As you'll see there, I've actually placed a marker signal ruler at 36 hertz, so PicoScope is frequency coupled. And theoretically, if we've got our maths right, when we run the cooling fan, we'll see that top speed, or peak vibration, occurs at 36 hertz. Could you run that, please? Okay, if we switch the cooling fan off now, if we just pause the software at that point, we can see how the frequency climbed as the speed of the fan increased and topped out approximately 36 hertz. If we do the maths on that, 36 times by 60, the cooling fan 2,160 RPM. So another way, Frank, of qualifying the frequency speed of a component.
Sure. It may be worth mentioning also that your channel input command has been set not from AC, DC, but to frequency to obtain this information.
Yeah, the frequency coupling of PicoScope, so that's available in the current 4000 and previous 4000 generation of PicoScope.
I think the really interesting thing I've picked up from this bar graph is that we can clearly see on the right-hand side that this frequency of around 35 Hertz sits quite nicely between E1, E2, so we know it's not the engine. And I think the way I'm thinking at the moment is, if we increase the frequency of the engine, there could be a situation where we get resonance, where we get two forces out of balance which add together. But looking at it in this way, we're able to separate this issue and see very clearly that this is a non-engine related component causing this problem.
So we had concentrated on the frequency view. This is exactly the same data, no different, but in bar graph view, where we've used the software to highlight the known vibrations on the left and the top 5 unknown on the right. In this scenario we had 39 Hertz. Remember, cooling fan frequency would be dependent on battery voltage as well. So if we are going to run the cooling fan for simulation, battery voltage is key for RPM.